students. Today we have Proposition 12 of Book 2, okay? It's about obtuse angle triangles. In obtuse angle triangles, the square on the side subtending the obtuse angle is greater than the squares on the sides of the obtuse angle by twice the rectangle contained by one of the sides, namely that on which the perpendicular falls when it's extended, and the line cut off outside by the perpendicular towards the obtuse angle. I'll explain it in a bit in the concrete, but first let's get clear on a couple of things. This is an obtuse angle because it's greater than a right angle. Obtuse means greater than a right angle. Obviously, we see that in the definitions. And just something for you, it was a little bit hard for me in doing this prop, but then I just thought about it. 5 is equal to 3 plus 2, say, or you can also say 5 is greater than 3 by 2. 5 is equal to 3 plus 2, 5 is greater than 3 by 2, 5 is greater than 2 by 3, okay? You're just gonna have to have that concept, okay? So here's our triangle, and here's the obtuse angle. Let's do something like this. Here's the obtuse angle, right? So this is the side subtending the obtuse angle. Thus, it is required to show that the square on this line is greater than the square on this line plus the square on this line by twice the rectangle contained by this line and the line produced from that point up to the perpendicular. So let's continue this line here. Okay. And I guess I'll just draw it straight like this, just to emphasize that that's the line produced. Okay? So, we drop the perpendicular. We know we can do that. We prove that 2 is from a point not on a straight line to drop a perpendicular. Okay? What we're going to prove now is that the square on this line is greater than the square on this line plus the square on this line by twice the rectangle contained by this line and this line, okay? So you just pick one of the sides, in this case we pick this side, and we extend it, and from the point on the other side we drop the perpendicular, and that'll give you the line that makes up the other part of the rectangle. So repeat, the square is required to prove that the square on this line, this is our original triangle, this is the original obtuse angle, this is a line subtending the obtuse angle. Thus it is required to show that the square on the side subtending the obtuse angle is greater than the squares on the sides of the obtuse angle by twice the rectangle on one of those sides, and the other side being the side contained, the side made up by the extension up into the perpendicular falling upon it. Okay? So the square on this is going to be greater than the square on this and the square on this by twice the rectangle contained by this line and this line. Now remember from the previous proposition, I don't remember which number it was, 12 in book 2 or something like that. If you have a line and it's cut at random, this is our black line. Part of it's dashed, part of it's solid, but it's one line. If you have a line, you cut it at random, the square on the whole line is equal to the squares on the parts, added together, plus twice the rectangle contained by the parts. It looked like this. Cut it, draw it, rectangle, boom. But the square on the whole line is equal to the squares on the parts, this and this, by twice the rectangle contained by the parts, this and this. This is contained by this and this, okay? That's it. You should go look at that other prop. There's no way you can really do this if you don't understand that, because the mind needs to hold that as true, otherwise you're not going to get it. So, the square on this, back to it. The square on this is equal to the square on this plus the square on this plus twice the rectangle contained by this and this. But look, let's add the square on this to both sides of that equation. Therefore, the square on this plus the square on this is equal to the square on this plus the square on this plus the square on this plus twice the rectangle contained by this and this. Okay? But look, the square on this and the square on this is equal to the square on this because this is a right angle triangle, another right angle triangle. So then we can say the square on this is equal to the square on this plus the square on this plus the square on this plus twice the rectangle contained by by this and this. But the square on this and the square on this is equal to the square on this because this is a right angle triangle. So then we can say the square on this is equal to the square on this plus the square on this plus twice the rectangle contained by this and this. Get that? So the square on this is equal to the square on this and the square on this by twice the rectangle contained by this and this, which is another way of saying that the square on this is greater than the square on this and the square on this by twice the rectangle contained by this and this. Okay? So, we just showed that in an obtuse angle triangle, the square on the sides subtending the obtuse angle is greater than the squares on the sides by twice the rectangle contained by one of those sides, namely that upon which the perpendicular falls when extended, and the line cut off outside all the way up to the obtuse angle. That is to say, twice the rectangle contained by this and this. Therefore, we have shown that in an obtuse angle triangle, the square on the sides subtending the obtuse angle is greater than the squares on the sides by twice the rectangle contained by one of the sides, namely that upon which the perpendicular falls, and the line cut off by the perpendicular outside towards all the way up to the obtuse angle. Quod erat demonstrandum. Thank you so much. Bye-bye.